Okay, I wanted to do at least some recording for forces today, so we are going to talk about forces and free body diagrams. This is not the end of forces, this is just the beginning for it. We're going to talk specifically about tension and normal force while we're here, and the use and reason why you'd want to do a free body diagram. So first off, what is a free body diagram? Well, if you imagine you have something like a box sitting on a table, and let's make that the table, and then we'll put a box on it. The free body diagram would represent the forces that are acting on this box. So in this case, it's sitting on a table. It would be experiencing likely a normal force and a weight, which would usually be something like mg. And if it's sitting on a tabletop like this, we'd also know the acceleration is likely going to be 0. So the free body diagram is just representing the forces that would act on a particular body, in this case, the magenta one. Okay, it gets more interesting if you start stacking things on top of each other. So you could imagine if you had a box sitting on another box sitting on the ground. Well, now we have a couple different objects here. We've got pink on top and blue on the bottom. If you wanted to start drawing forces, we'll call these 1 and 2, we'll number them. So here's our object number 1. Well, it would be experiencing a normal force, and that normal force would be between 1 and 2, and then it would have its weight. And if we try and represent the forces that are acting on the second one, it would have a couple different things. One would be a normal force due to the ground, and then there would be normal force 1, 2, because they're pushing against each other, and normal forces will always act between pairs of objects. And then, of course, we'd have the weight of our second object, m2g. So, free body diagrams, you're just trying to represent the forces that are acting on a particular body. So let me give you some rules for that. The forces should always point in the direction they act, with the tail end attached to the body. So notice I always had the tail end of my vectors attached to my point. Okay, another rule. Use length to indicate strength. So if you know they're going to kind of balance out, you should draw them about the same length. If you know that there are multiple forces acting in different directions, make sure you draw them so that if they're supposed to cancel out, they about add up to the right thing to cancel out. So let's see. Only draw forces that act directly on the body. Let me come up to this picture again. You notice on object number 1, I did not draw normal due to the ground. That's because the ground does not act directly on the upper body. That's really important. Okay, I'm going to give you a couple more rules. These have to do with different types of forces. Normal force always acts at right angle to the surface that makes it. So it is always, always, always perpendicular. And let's look up at the picture again, because there are a couple things that might surprise you. Here, the surface that's creating this N12 on the upper one is this surface right here, the upper surface of the lower box. So that means the force will act at right angles to it. It would act upward. Okay. You notice that when we're figuring out the forces acting on the lower box. Now, the surface that's creating the normal force is here, the bottom surface of the upper box. It will be downward and perpendicular to that lower surface of the box. Let's continue. We have a force normal due to the ground. That's going to be a force due to this surface acting on the box. It will make a right angle to that surface and be acting upward. Okay. I changed the color without intending to. All right, continuing. Tensions will only act on the objects they attach to. Furthermore, the rope can redirect the force. So, as an example of the weirdness of tension, if you have a pulley and you have a couple of boxes hanging from said pulley with ropes used to attach them. Oops, I don't want a rectangle for that. Then it's going to wrap around, and the way the force will actually act is up on each box. If we consider how the tension acts on the pulley, the tension would be acting down on each side of the pulley. Yes, this can get a bit confusing. I suggest when you have things like this and you're doing tensions, you consider putting some little marks around the object you're interested in. When you start doing that, it will become more obvious which forces are directly attached to that object, making it easier to identify the forces that belong in your free body diagram. Okay, I do want to mention two more forces before I end this video and we get into more detail with what we can do with free body diagrams. Friction. The just standard friction force has a size of mu times the normal force. If static, then it can have a size from 0 up to mu static times the normal. And the normal matters, which surface you're attached to. So if we're thinking about a box and we are pushing it up against a wall, we are providing a force F acting on it. The way the forces are actually going to end up here is the force of me pushing is towards the right. The normal force is actually back towards the left. Gravitation is downward, and the friction force, which I'm doing a lowercase f for, would actually be acting upward here. Okay, other thing to notice about friction. Friction is parallel. I misspelled friction, let me fix that. To the surface that creates it. So here, notice that the surface is up-down, the friction force is also up-down. If you had a box sitting on the floor and you were pushing it to the side, when we go to draw that one, we'd have our force to the side, our friction force back the other way, with normal being upward and gravitational being downward. So have a care with that. Normals are perpendicular to the surface that makes them. Frictions are parallel to the surface that makes them. All right, last force I want to mention for the time being is the spring force. Spring force has a size that looks something like minus kx. This will always be the force due to the spring. If you want to know the force due to the thing pulling on the spring, it may be different. So keep that in mind. Also, the x is important. Springs have a natural length x. They'll only exert forces if they've been stretched beyond that point. I should actually say this is natural length. X equals 0. And here, we've stretched it out by a distance x. You can, of course, also compress it, in which case you'd have some distance. I won't write minus x. It would be negative in this case, however, because you've made it shorter. And the positive negative thing does depend on your 0 point. So it depends on, well, actually it's the coordinate system. Okay. Pardon me. So that's some introductory material. The next one, we're going to try a few more interesting cases of objects interacting with each other. Maybe do a couple examples, and that will be a good lead-in for the practice sheet that I've got. We'll also work on taking free body diagrams and turning those into Newton's second law equations. I'll remind you right now, though, Newton's second law is the sum of forces equals ma. All right, that's going to be it for this first one. See you in the next.